In this video, what we're going to do is we're going to fill out table 5. And for that, we're going to figure out what the rate constant is for the rate law. So recall the rate law is rate equals K times the concentration of H2O2 raised to the M times the concentration of Ki raised to the N. For this experiment, we're doing the initial concentrations. Okay, so let's begin. We have 5 experiments. So the first thing we're going to do is we're going to come back and put in the initial concentrations of H2O2. So the initial concentrations right here. Okay. And then we'll just fill that down. Okay. So notice again, just, when you're filling out tables like this, it's a good idea to check the first 3 experiments, the concentration was the same, and then it started changing, and you just check to make sure the numbers are the same. The next thing we're going to do is we're going to raise it to the m power. Now, we figured that out in the previous table, table 4. So I'm going to hit equal sign this, and then to raise it to a power, use the little caret symbol, which is options, or it's shift 6. And then I'm going to come over here, and I'm going to find our m value, which is right here, 0.95. Okay. But again, if you recall, what we said before was that if you want to use just one value in a table, you put the dollar sign. So $C, $18. Okay, and then fill that down. Again, we don't need so many significant figures. So let's bring it back a little bit. Bring it down to, say, 3. All right. There's our initial concentration of H2O2 to the m's. Good. Excellent. Now we do the same thing for Ki. So the initial concentration of Ki, we go back all the way over to table 3. And, oops, sorry, table 2. Initial concentration of Ki, here it is, 0.02. Okay. And we're going to fill that down. There we go. Again, concentration's changing and then not changing. Equal sign concentration raised to the n. And the n we found in the previous table, 0.94. And then again, we'll make this $F, $18, which will ensure that for all those calculations, it's using the same value. Okay, we don't need to have that. There we go. Okay. The next thing we're going to do is we're going to find the initial rate. Well, the initial rate, we have that already from the previous table, so equal sign. Well, that actually is table 3, the rate, right? So the rate is right here. Okay, so table 5, there's our initial rate. Okay, all right. And again, you just want to check, make sure, see how this is the smallest, it gets bigger, gets bigger, gets bigger, gets bigger. Okay. Now we're going to find the rate constant. And the way we find the rate constant is we use this formula here. We're going to take, to find K, we're going to take the rate and then divide on both sides the concentration of H2O2 raised to the M times the concentration of Ki raised to the N. So we're going to divide by that entire chain there, okay? So that the way we do that then is to say equal sign rate divided by, and I'm going to put it in parentheses, H2O2 to the M times, so shift 8, Ki to the N, close parentheses, and that looks good. Okay. Now notice what we get here. If you look at those values, they're all relatively similar, right? 6.39 times 10 to the minus 3, 6.8 times 10 to the minus 3, 6.32 times 10 to the minus 3. They're pretty close to each other. So when we have multiple measures of the same parameter, we can do just an arithmetic mean. So equal sign average. And then I'm going to type out, you have to actually type out all the way average. Parentheses, highlight the cells you want to take the average of, close the parentheses. And there you go. So there's our average, right? So that's an important value. That's one of the things we were trying to do in this experiment, was to figure out the value of the rate constant. Now we can also do a statistical study of the standard deviation, which is essentially a measure, a parameter that tells us how close those 5 values were to each other, how close to the mean they are, essentially. So I'm going to type in STDEV, parentheses. So that's standard deviation, STDV. Just do those 5 measurements. Okay, let's get rid of some of those sig figs. And let's put it into, actually, let's go ahead and put it into scientific notation. There we go. Looks good. Okay. So if you look at the standard deviation, it's quite a bit smaller than the average, than the mean. So that's good. You want the standard deviation, the smaller the better. So this is quite a bit smaller. This is actually, if you actually, you can, here's a way just to do it. Take the ratio. You can do the ratio of the of the average divided by the standard deviation. So if I do that, it's a factor of almost 30, right? 29.2. Almost, 29. So it's 29 times bigger. So that means those values are pretty close to each other. Again, I made those numbers up. I made the times up. So I picked numbers for the times that would give us good results. Your results may vary. Okay. All right. So there you go. So there's your table. So now what we would do is we would say, hey, we know what the rate is, the rate law. The rate would be, I'm going to put in parentheses, 6.42 times 10 to the minus 3, so that's your K, times the concentration of H2O2 raised to the, now you can put 0.95, but at this stage, really what you could do is you could just say, hey, look, it's to the first power. It's pretty close to 1. We'll round it at this stage. So times concentration of Ki. Again, that one is like 0.95 or something like that. It's pretty close to 1. So they're very, we'll just put 1 in there. And so that would be our rate law. Okay, we now know that it's first order in H2O2, it's first order in Ki with a rate constant of 6.42 times 10 to the minus 3. In fact, since we know that it's first order in both of the reactants, that means we would now know that overall it's second order. So the units would be molarity to the minus 1, seconds to the minus 1. We now have the units of the rate constant as well. So now we have completed part 1. We have determined the fully the rate law at room temperature for this particular reaction.